Bismillahirrahmanirrahim. Um, Good morning, students. Welcome to the new lecture for Introduction to Information Technology. So far we have discussed about in the first chapter about the general introduction of computers, and in the second chapter that we have started, and this is the third lecture from the chapter number 2 to understand the system unit, right? So first we discussed that how we can code, how we can represent, how we can convert the instructions to the computer by converting in different into the machine language in the binary numbers, right? And we discussed different strategies and coding mechanisms there. And then we discussed that what components are available inside a system unit, right? And we have a detailed lecture in the last week, in the previous lecture. So today we will be discussing about how the central processing unit, how the CPU actually works, right? So as discussed earlier, a CPU consists of a variety of circuitry and components packaged together, right? So the main key element of the processor is the transistor. So a transistor is basically a device made up of semiconductor material that controls the flow of electron inside a chip, right? So today's CPU contain hundreds of millions of transistors, and the number doubles approximately every 18 months. So this phenomena is known as the Moore's law, and we will discuss it in the next slide. So the primary component of a typical CPU is also discussed in the coming slide, right? So basically, what is the Moore's law? Moore's was a scientist in 1965. He gives a law. The Moore's predicted that the number of transistors per square inch on a chip had doubled every 2 years, and that trend will continue. So Moore's law is still relevant today for processors as well as other computer components, right? So it says, so the number of transistor is what we discussed in the previous slide. Transistors are they actually, they are the semiconductor material that control the flow of the electron inside a chip. So remember from the previous lectures that transistors were used in the second generation of the computers, right? And we are still using these transistors in modern CPUs, right? So the use of the transistor per square inch are being doubled every 2 years. And that means the speed of the processor is being doubled, right? So the typical components of a CPU, let's go directly to this slide. Here you can see in the diagram, we have several components, right? So to begin, okay, so to begin to understand how a computer CPU works, you need to know how the CPU is organized and what components it includes, right? So this information will help you understand how electronic impulses move from one part of the CPU to another to process the data. The architecture and components include in a CPU, we usually refer it as the microarchitecture. It varies from processor to processor. A simplified example of the principal component that might be included in a single core of the typical CPU is shown here in this figure, right? So what are those components that are included in single core of the processor? If there are multiple cores, every core will have these components. What are those components? The ALU and the FPU, arithmetic logical unit, and the floating point units, right? A control unit. We will be having the detail of every component in coming slides, right? Well, we have the prefetch unit, we have the decode unit, we have registers, we have bus interface unit, we have the internal cache memory. Most of the terminologies you are already aware from the previous lecture. We'll be discussing these components in detail one by one in the coming slides, right? So let's move back here. So normally the arithmetic and logical unit, right? So the first component, the typical CPU components, the first component that we are going to discuss from this diagram is arithmetic logical unit, right? Or the floating point unit and the floating point unit. So the arithmetic logical unit is the section of a CPU core that performs arithmetics. What do we mean by the arithmetic? The mathematical operations, the addition, subtraction, multiplication, and division, right? It all that it all the arithmetics that involve the integers and as well as the logical operations. What are the logical operations? Such as comparing two pieces of the data to see if they are equal or determining if a specific condition is true or false. So if we are comparing two numbers, this is called the logical unit. Or we say that we need to check whether this condition is true or false, that is the logical unit. But if we are performing addition, subtraction, multiplication, division of the integers, that is called the arithmetic operations, right? So ALU, arithmetic logical unit, it performs arithmetic that involves integers and all the logical operations, right? So, so the arithmetic requiring decimal is usually performed by the floating point units, FPU. So, if we have the floating point numbers, that the number that involves the decimal values like 3.5 plus 1.9. So, such numbers, such arithmetic will be performed by floating point unit, right? So, when many other common computing tasks are performed, for example, editing a digital photograph in an image editing program, running the spell checker in a word processor program, and burning a CD, music CD, and all performed by the ALU with help from the FPU when needed. So using only arithmetic and logical operations, most CPUs today have multiple ALUs and FPUs that work together to perform the necessary operations, right? So all such type of operations, including the graphics, writing CD, spell check, whatever the operations are performed, they are being performed by ALU with the help of the FPU, right? So the control unit, the second, the most important component, the control unit coordinates and control the operation and activities taking place within a CPU core, right? Such as retrieving data and instructions and passing them to the ALU or FPU for execution. So actually control unit control or and coordinate all the activities within a CPU core, right? So in other words, it directs the flow of electronic traffic within the core, much like a traffic cop controls the flow of vehicles on a roadway. Essentially, the control unit tells the ALU and FPU what to do and make sure that everything happens at the right time in order for the appropriate processing to take place, right? Then next is the prefetch unit. So the prefetch unit orders data and instructions from cache to RAM based on the current task. The prefetch unit tries to predict what data and instruction will be needed and retrieves them ahead of time in order to help avoid delays in the processing. So basically, prefetch unit attempts to retrieve the data from the RAM to the cache memory, right? So that the instructions before they are needed for processing in order to avoid the delay. So that's the functionality of the prefetch unit. Decode unit. So the decode unit takes the instructions fetched by the prefetch unit and translates them into a form that can be understood by the control unit, ALU, and FPU. The decode instruction go to the control unit for processing. We already discussed this in the last class, that whatever the instructions or the softwares even you are running, those instructions need to be bring into the processor, and it should be decoded in the machine language or the instruction set of that processor, so that ALU, FPU, and the control units can understand those instructions and then they can be executed, right? Next is the registers and the internal cache memory. We already have discussed these two important concepts in the last video lecture. So registers, they store data and instructions nearby needed by the CPU, right? So registers hold the data that are the intermediate results of two calculations, and cache memory holds the data or the instructions that are needed by the CPU, right? Okay, so the bus interface unit, it allows the core to communicate with other CPU components, right? So there are many components of the CPU. We already know that bus is but actually a pathway on which the electronic data and the electronic signals flows, right? So the bus unit interface is the interface where all the other components like RAM and other components of the CPU, the input output devices, all other are connected. So it allows, the bus unit allows them to communicate among with each other, right? Okay, the system clock. So the system clock is made up of small quartz crystals that are located on the motherboard, right? In order to synchronize all of computer's operations, a system clock is used, right? So the system clock sends out a signal on a regular basis to all other computer components, similar to a musician's a metronome or a person's heartbeat. Like our heart beats every, I mean, one beat, and it synchronizes all the components. Each signal is referred to as a cycle. The number of cycles per second is measured in hertz, right? 1 megahertz is equal to 1 million ticks of a system clock. Okay, so many personal computers today have system clock that run at 200 megahertz, and all devices that are synchronized with these system clocks run at either the system clock speed or at a multiple of or a fraction of the system clock speed, right? For an example, a CPU with a CPU clock speed of 2 gigahertz uses a multiplier of 10, meaning that the CPU clock essentially takes 10 times during each system clock tick. During each CPU clock tick, the CPU can execute one or more pieces of microcode. Virtually all CPUs today can process more than one piece of microcode at one time. It's a characteristic known as a superscalar, which is the ability to process multiple instructions per cycle. A CPU with a higher CPU clock speed processes more instructions per second than the same CPU with lower CPU clock speed, right? So it basically synchronizes the computer operations at every tick. It synchronizes each signal, or each tick is measured in the cycle, and the unit is the hertz, right? So, okay, as discussed, so many PCs, I mean, they run on 200 megahertz. So one example that I discussed earlier. So if a CPU clock speed of 2 gigahertz means the CPU clock ticks 10 times during each system clock tick, right? So during each CPU clock tick, one or more piece of microcode are processed. Microcode are the instructions that are executed by a central processing unit. The CPU with a higher clock speed processes more instructions per second than the CPU, the same CPU with a lower clock speed, right? So, okay, let's discuss about the machine side. Whenever the CPU processes a single piece of microcode, it is referred to as a machine cycle, right? Whenever one microcode is processed by the processor, this is referred to as one machine cycle. So Each machine cycle consists of the four general operations illustrated in here in this figure, right? So every machine cycle is consists of these four operations. What are those operations? Fetch, decode, execute, store. These are the four steps. These are the four instructions, operations that are processed at every machine cycle, right? So what do we mean by the fetch? Fetch is the program instructions is fetched from RAM, from memory to the or from the cache inside the CPU. So the instructions are located in cache memory or in the RAM. So the fetch at every machine cycles step fetch, it will fetch the instruction inside the processor, the CPU. Then decode, the instructions are decoded so the control unit, ALU and FPU can understand them. So we discussed it already. All the instructions that are fetched will be decoded into the instructions based on the instruction set of the architecture of the processor. They will be decoded so that ALU, CU, FPU, they can understand those instructions, right? And as a step number 3, it will execute those instructions, right? So the instructions that are decoded, they are carried out. And finally, at the step number 4, it stores the original data or the result from the ALU or FPU execution is stored in the CPU's registers. So the results that are computed are stored back to the RAM from the register to the RAM or to the cache, right? So these are the steps, four operations involved in the machine cycle. Fetch means fetching the data from fetching the data inside CPU, decoding the instructions, executing the instruction, those instruction, and the final one is storing the result back to the RAM or to the registers, right? So because each machine cycle processes only a single microcode instruction, many seemingly simple command might require more than one machine cycle, as a computer might need to go through thousands, millions, or even billions of machine cycles to complete a user command or program instruction. For instance, a CPU processing the command 2 plus 3 would typically require at least 4 machine cycles for if we want to add 2 plus 3. So it requires 4 machine cycles. What are those? At number 1, fetch the number 2 from RAM, decode it and store it in a register X, right? So first of all, what will happen at the first machine cycle? It will fetch number 2, right? If we want to add 2 plus 3, it will fetch 2 from the RAM, it will decode it, it will store it in the register, right? In step number and in the second machine cycle, what will happen? It will fetch number 3 from the RAM, decode it and store it in register Y. So the second number is fetched into the CPU, it is decoded based on the instruction set, it is stored in the register Y. Now the third operation, or on the third machine cycle, what will happen? Fetch and decode the addition instruction. What do you want? If you want to add, so it will decode, fetch the instruction that what you want to do with two number that are stored in X and Y registers, right? So fetch and decode the addition instruction, then add the two numbers, right? And store the result in register Z, register Z. So at the third machine cycle, it fetched the addition instruction, decoded that instruction, executed that instruction on X and Y and stored it in another register Z, right? So one third machine cycle is complete. At the fourth machine cycle, it will fetch and decode the instruction to display the sum and then output the sum to the RAM. So it will see how to show the result, fetch that instruction, decode that instruction, execute that instruction, and store the result back to the RAM, right? So this is how the machine cycle works. At every machine cycle, 4 operations are performed, and in order to perform one operation, several machine cycles may be involved, right? Okay. So now let's see how we can improve our the performance of our computer system in today's. So if you have a older computer, you can always improve the performance. Usually, we in the older computer systems, as time passes, the application require more computations. But if you are using the modern applications on the older computers, the performance may compromise, right? It's similar to that. You are playing the high performance games of today's in the older smartphones, right? With the low memory, with the low processing power and all these things. So what we can do if we have the older computer and we want to make it the performance better of our system. So there are several approaches that we are going to discuss now. The first approach is add more memory. So if check the memory of your system, the RAM, if it is less than 4 GB and you are going to run the applications on that, it's better to have at least 4 GB of RAM. Or if you can add more RAM to your system, that will boost the performance of your system. Remember, CPU will only process the instructions when it will fetch the data from the RAM. So if RAM is slower, it cannot hold much data. So doesn't matter if you have a high speed CPU, it will only process the instructions that are available in the RAM, right? So RAM memory, if you add the memory, the performance of the speed, your computer will become better. But before adding the memory, just open your system and see if you have available slots to add more memory inside. So if there is a slot, you can always add the memory to improve the performance of your system. Another aspect is do the system maintenance, right? Most of the time when we install or uninstall the different programs, or whenever we are going to install the program and uninstall the program, most of the files still remain on the hard drive or in the system. That degrades the performance of your computer system. So whenever you are going to uninstall some activity, some program, so uninstall it properly. Just do not delete the files, uninstall it properly. If you are using the Microsoft Windows, go to the control panel and uninstall the programs in a proper manner, right? This will improve the performance of the system. Also, if you have some programs that you are not using frequently in your computer system, and they are in the startup list. So whenever startup list means whenever your computer is start, those programs starts automatically, and then it slow down the booting process of the system. So if you do not want to compromise the performance of your system, better to have the minimum programs in the startup list. So remove unnecessary program from the startup list, right? And one of the most important aspect is when you store large files on the on your disk, right? Very huge files, very large files on the disk, and you rarely use them. Most of the time, the files are stored on the disk in small fragments, right? Small pieces. And when you retrieve the data into the RAM from the disk, they are actually gathered, they are being read from different locations of the disk, and they are loaded into the RAM. We will study this phenomena in the next chapter, chapter 3, right? So those files are stored in the fragments, and when you actually accessing those files, the large files, they are not that you rarely use, but the disk is full, so that also degrade the performance of the system. So what is the alternative way? Alternative way is use such large files that you do not use on the regular basis. Store them on some external drive, some external hard disk, or some external USB drive, pen drive, and load them whenever you need it. And also one of the important aspect is delete the temporary files. So temporary files usually slow down the system. How you can do that? If you are using Microsoft Windows, go to the run box or the search box, just write it temp, TEMP, and one folder will be opened. In the folder, you will see a lot of temporary files that are that you have used some programs and they created their temporary files. You have terminated those applications, but their temporary files are still there. So it's always better to delete those temporary files. Another thing, how you can do this thing is, we have one utility in the, if you can see this picture, this is called disk cleanup, right? So you can always clean up your disk, that will delete all the unnecessary files from your system automatically, and a lot of space can be freed. For example, it says 1.93 GB can be freed up, right? So I mean, you can use all these things, right? um, Always check for the errors and defrags the hard drive periodically. As I told you that most of the time the data stored on the disk are in fragments, so you need to defrag the disks periodically. But nowadays modern operating system, they automatically do the defrag after some time, so not a problem. But do check for the errors. If there are some errors in for that pertain your system performance, that I mean that are the hurdles for your system performance, right? So scan for the viruses regularly and the spywares, right? What is the difference between virus and a spyware? Viruses are the bugs, basically the code that actually slow down the system performance, that replicate itself on the disk and the memory. Spyware are the software that actually spy your data and related private information and send back to other people. But we will see what are the viruses and what are the spyware in detail in the coming lectures, and we will also see how to protect ourselves from such intruders, right? So clean out dust once or twice a year. Open the system box, use a blur to clean the dust from the system. Okay, so buy a larger or second hard drive. I mean, if you have a small hard drive, definitely that is going to compromise the performance. Upgrade your internet connection, for sure. If better the internet connection, your system performance will be better. Upgrade your video graphics card as well. This will also, I mean, the better the graphics card, the better the GPU will be, the better the processing, right? Now, making computers faster and better now and in the future. So what are the what we are using now and what are the future trends? So there are several strategies for making faster and better computers. One is scientists and the researcher are continuously improving the architecture of the computer system. What do you mean by the architecture? I mean, the components are getting smaller in size, the bus speed is getting faster, multiple CPU cores are being added, and virtualization support is also enabled for the modern architecture, so that the system can perform better. So faster the speed, we already discussed these things, right? More the CPU cores, faster the CPU base, better the memory, and obviously the system will be improved. So this all involved in the system architecture. So if you see, every system have its own architecture, and the modern system, whatever is coming, and in the future, the researchers are continuously working to improve the architecture of the system. Another aspect is improving the materials. So far what we are using are the semiconductors, right? Silicon material for for producing the chips, for producing the CPU chip and the memory chip. So now the future trend is to move towards the copper, to try the copper and high K graphene chip and all these things, in order to improve the material for flexible electronic components. So this is one of the example you can see. This is a flexible electronic, I mean, using the copper and the other graphene chip. I mean, this is how we are going to produce the chips in the future. So experiments are has been done. So maybe in the future we have the flexible components. Pipelining, it allows the multiple instructions to be processed at once. Let's have a look on this diagram. So if we do not implement the pipeline, what will happen? We already know that in order to process one instruction, one machine cycle, what it does fetch, decode, execute, and store. So this has to be completed, and then the next instruction, in the next machine cycle, next instruction will be completed, right? In order to, uh, I mean, for example, when the at one machine cycle it will fetch. In the next machine cycle, this fetching process will be idle, right? The code will execute, right? So in the next machine cycle, decode and fetch both will idle, and execute will be executed. And in the fourth machine cycle, all these three will be idle, and fourth result storage will be active, and this will perform its work. And the next machine cycle, then only fetch will be executed, rest of the three will be idle. So in order to utilize it, in order to get the maximum throughput, what is the phenomena? We use the pipelines. Pipelining means, so when this is when it starts, first instruction it fetch, next machine cycle when it will start decoding, it fetch the next instruction. So this fetch will not be the idle at this point. Now it will fetch the next instruction, and at the third machine cycle, when this decoding instruction will be executed by the execute step, right? So this decode instruction will be executed on the this fetched instruction. So decode will not also be the idle at this point, and this fetch will fetch the third instruction in the CPU. So, and when this will the result will be storing the result for the first instruction. So the second instruction will be executed at time, and this instruction will be decoded, right? Whatever we have fetched here, and the next fourth instruction will be fetched. So this is a concept of the pipeline, that with the pipelining, a new instruction is started when preceding instructions move to the next stage of the pipeline, right? So it allows multiple instructions to be processed at one time, right? So multiprocessing, this is another strategy for making the computer faster. That is the multiprocessing and the parallel processing. It uses the multiple processors to speed up the processing. But these two terms are different, multiprocessing and parallel processing. What is multiprocessing? Multiprocessing is where each processor or core typically works on a different jobs. So each core or each processor, they are working on different jobs, different instructions. So this is the multi-processing. Multiple processes are executed by multiple cores. Whereas in the parallel processing, uh, where multiple processors or cores work together to make one single job finish sooner. So that's the concept of the parallel processing. Multiple processes are there, they are processing all together but on a single job. But if they are processing the multiple jobs at the same time, this is called the multi-processing, right? Okay, next, future trends. So future trends are nanotechnology. So we already know that what is nanotechnology. This is the science of creating tiny computers and components less than 100 nanometer in size. So we can observe this, we can witness this, that the size of the chips, the size of the computer, the size of the electronic gadgets are becoming smaller and smaller. Who is enabling this? That is the nanotechnology, right? So carbon nanotubes used in many products today, right? Nano filters and the nano sensors are being used. Future applications may be built by working at the individual atomic and the molecular level, right? Okay, so then we have the concept of the magic glass. That is another technology implemented by the MIT. So MIT's glass is basically the MIT has developed a nano-sized canonical pattern on the surface of glass to eliminate its reflective properties. Here, if you can see in this diagram, this is a normal glass, right? And this is the glass manufactured by the MIT. So the MIT Magic Glass, if you can see the normal half of the glass, if you have some text over it, it can be foggy. It can have a glare surface. Because of the glare surface, it is foggy. Whereas in MIT's glass, MIT's nano glass, they have basically the clear text on that, right? So glass resist fogging, and it's is self-cleaning, right? So there are possible uses of such glass that is developed in future. One is the smartphone screens, right? eyeglasses. On the eyeglasses you can program it and you can display text and other material over there. Televisions, car windshields. So on the windshield you can give the instructions, or clear windscreen for without fogging for the car drivers. You can build the windows with this magic glass as well. Another future trend is the quantum computing. So it basically applies the principle of quantum physics and quantum mechanics to computers, right? In order to compute different tasks. So it utilizes atoms or nuclei working together as quantum bits, or in short we call it qubits. So qubits are in normal computers we have bits. In the quantum computers we use the qubits. So qubit functions simultaneously as the computer's processor and memory can represent more than two states at the same time. What is the concept of the quantum? Quantum, you can have multiple states of the same object at the same time, right? So that is being utilized. That is the concept of quantum physics that is utilized in the quantum computers, right? So expect it to be used for specialized applications such as encryption and code breaking. Optical computing. Optical computing, they uses light from laser beam or infrared beams to perform digital computations. Optoelectronic computers, they use both optical and electronics components altogether. So this is again a future trend. Maybe in near future we will be having optical computers as well. Silicon photonics, uh, the the process of making optical devices using silicon manufacturing techniques are called the silicon photonics. So possible low cost solution to future data intensive computing applications, telemedicine, cloud data centers, and for those equipment, the phonetics will be the silicon photons will be the solution, right? Parascale computing is the ability to, again, this is the future trend, is the ability to process 1 trillion floating point operations per second. Now you can see, we also refer it teraflops. Teraflops mean trillions of floating point instructions per second. So you can imagine the speed of the computer, right? So Terascale research is focusing on creating multi-core processors with tens of hundreds of cores. Obviously, in order to have trillions of flops, teraflops at these per second, we require hundreds of cores of the to process altogether. Intel has created a single chip cloud computer with which contains 48 cores on one silicon chip. So Intel has already developed one processor, one single chip with 48 cores, and still research is going on to move it to the hundreds of cores. Expected to be needed for future applications. Obviously, future applications are data intensive, computing hungry applications, so they require these type of things. Another future trend is the 3D chips. 3D chips, they contain transistors that are layered to cut down on the surface area required. So what happens if we in the today's CPU or today's chip, we can say we have one square or one, I mean, all the transistors are placed and more space is being occupied. So instead of having this, we are having multi-story of the transistors, right, in the 3D fashion. So what can happen? We have the multiple layers at the ground layer or the ground floor. We have one layer of the transistor. Then we have silicon wafer. On top of that, we have another silicon, list of layer of the transistor. Then we have the silicon wafer in order to avoid the conflict and to absorb the heat. We have more. I mean, in this way, the 3D chips are being developed so that the size can be reduced and the performance can be better. So being used with the memory, flash memory, and CPUs, we are using these. We are developing these 3D chips, right? So that's all about this chapter. What we have learned in this chapter from the last three video lectures. In the first video lecture, we discussed about the data and the program representation. In the second lecture, we saw what is inside the system unit. And in this lecture, we saw that how the CPU actually works, what is the machine cycle, how it works, and then how we can make our computer faster and better in now and in the future. We saw different future trends, and we saw that what we can do with our existing computers. All right. So that's all for this lecture. We'll see you in the next lecture with the storage devices. All right. Take care. Goodbye.